right, last type of approximation in our artillery today. We're going to talk about trapezoidal approximations. And this kind of goes nicely with the same, principles of the rectangular approximations and Riemann sums that we did at the beginning of the chapter. But we do it now at the end of the chapter, just because it's different on a couple levels. And I think if we introduce trapezoids at the same time as rectangles, you'd be massively confused. So I want you to take a moment to think about what the area of a trapezoid is. See if you can drum up that formula. Okay. Hopefully from the options you chose this. It's the height divided by 2 times the sum of the bases. Okay, and remember that when we look at a trapezoid, when we talk about the height of a trapezoid, we are talking about the distance between the bases. So this distance right here, the two sides that are parallel, that's actually the height of the trapezoid. So if the trapezoid is facing that way, the height goes side to side. If that trapezoid were laying down like this, or let's make it an actual isosceles looking trapezoid. This is probably how you picture it. When you picture an actual trapezoid, right, like this, the height is, makes sense to call it height because it's facing that way. So let's be clear when we do our first one about what the height represents. So we're going to do example 1A. We're actually not going to do B, I think, just to save time. So A, it says, find a trapezoidal approximation for the area under the curve of f of x equals 9 minus x squared over 0 to 3 using 3 subintervals. So this is still the n value that we had in the past, right? 3 trapezoids is what this is talking about. The first thing we're going to do to calculate the height of the trapezoid is the same as before. We're going to do b minus a, all divided by n, because these are going to be equal in height. So 3 minus 0 divided by 3 means each trapezoid is going to have a height of 1. And what I'm going to do on the right side over here is I'm going to put together a sketch, a sketch of this function here. This is not to scale, so let's be clear on that. Let's say this is 9 up here, and this is 3 and negative 3. So we have this upside down parabola that kind of looks like this, right? And we're embedding trapezoids in there. So we know that each one is going to be 1 unit wide. So the first one, I just want to sketch what that looks like. So between 0 and 1, we're going to draw a trapezoid that's as high as the function is at 0 and 1. So the first trapezoid is this pink guy. My phone. No one texts me until I make these notes videos, swear. Okay, so in this trapezoid here, we want to figure out the area of it. So the pink trapezoid would be, its height is 1 unit divided by 2, and then the bases are determined, right, by f of 0 and f of 1, however tall the function is at those 2 points. Okay. So that's the first trapezoid. We're not going to hardcore calculate that yet. Now we're going to do a second trapezoid between 1 and 2. Okay, and I want you to kind of notice what happens here. If I put dots on the function at 1 and 2, there's going to be this overlap between these next two, and that the left base of the green trapezoid is the same as the right base of the pink trapezoid. So we would say the area of the green one is 1/2 f of 1 plus f of 2. Like that. And then again, we're going to have this little sharing of bases in the trapezoid that exists between 2 and 3. So when I plug in 2 into the function, technically I get 5, I guess. If I plug in 3, I get 0. So this last trapezoid is technically a triangle. However, it does share the base with the green one, right? So when I write out the blue area, I have 1/2 f of 2 plus f of 3. Okay, and so those areas added together, right, is how we would calculate this area. But I want to kind of talk about a simpler way to write it. Not simpler, but just kind of the conventional way that we write it so that you can do it all at once. So I'm going to put that here in the, well, first thing I want to do with you is highlight the fact that you'll notice that all those bases, that f of 1, right, the base of the pink one and the green one, what they have in common, gets repeated in each of the area statements. And then, of course, let's do it in orange, f of 2, because that's a shared base, gets repeated in the area statements. So when we write out the actual area for this in total, what we do is we tend to double these inside bases. So double interior the bases, and I'll show you how that looks. So we would say the area, I'm going to just rewrite this different. I'm going to put the 1/2, the height, which would technically be 1/2, right? 1 over 2. And then I'm going to put that one time out front because they're all equal heights. And then I'm going to put f of 0 one time. I'm going to double the f of 1 that's highlighted. I'm going to double the f of 2 that's highlighted. And then I'm going to put that f of 3 in one time. So when I write this horizontally, right, you can kind of see I'm doubling those bases that get used twice. And it's just a shorter way to write it, you know, than writing out f of 1 plus f of 1 plus f of 2 plus f of 2. It's just kind of obnoxious to do that. So if you actually plug in all of the values, I think, to the function, this one is not too bad to plug in. Actually, let me write it underneath since we're skipping part B. We would say it's 1/2. If I plug in 0 to the function, I get 9 minus 0 squared, so that's 9. Plus 2 times, if I plug in 1, I get 9 minus 1 squared, which is 8. If I plug in 2, I think earlier we said we get 5. And then f of 3 we know is 0. That's why we had a triangle on the end. Oh, math. Okay, so what is this? 1/2, 9 plus 16 plus 10, 26, and 9 is 35 over 2. So this, right, 17.5 is what we would end up with for the area approximation. And what is nice to note about trapezoids here is that you can see when you look at the space between the function and the trapezoid, there's not a whole lot of room there. You can automatically tell that trapezoids are a better approximator than those rectangles because they tend to fit the curve better. Okay, so that's kind of a first thing to notice. All right, so if you have a function where you have to plug the x values in, that's how you're going to generate it. Examples 2 and 3, and actually the rest in this whole thing are from table of values. So in example 2 here, we're going to find a trapezoidal approximation from 0 to 8 of this function here in the table, given 4 subintervals. Okay, now as it says here, these are all equal in height, right? So I can tell that, remember, because the change in x in each of these values is 2 units. All right, so if we do b minus a divided by my 4, right, every trapezoid is going to be 2 units tall. So my area is going to be 2 over 2. I'm going to write that out because this is the height that I calculated. Oops, height. So then I put that here. Okay, and then in the parentheses goes the internal bases 12, 10, 5 get doubled, and then the ones on the ends only get used once. So when I put that in here, I'm going to do 20 plus 2 times 12 plus 2 times 10 plus 2 times 5 plus 3. Okay, and again, here are my interior bases being doubled, and then that ones on the end are just singletons, 20. You know, I have to overdo it here with the doubling and the interior, exterior colors. So there you go. This works out to be what? 20 plus 24 plus 20 plus 10 plus 3, 44, 64, 74, 77 units of area. Okay. All right, so now we're going to switch gears, and now the next example, in example 3 that we're going to do, is unequal heights. And we have a little experience again of doing this back when we did rectangles. So if I look down here, same principle as example 2, I just noticed that my change between all my x values here is different every single time, right? That change is not predictable and it's not the same. So what that means is I'm going to have to write out 4 different trapezoidal areas and add them all together. So you cannot mush it all in one big long string of arithmetic. You're going to do it individually. So this distance here is my height. So for my first trapezoid, it's 20 over 2, and then the sum of my bases is 0 and 3. Second trapezoid will be this distance here between 20 and 12. So that's a height of 12 units divided by 2, and then the sum of its bases are 3 plus 8. Next guy, let's go green, is 8 units in height. And then sum of my bases are 8 and 10. And then the last guy is 20 units in height. And then the sum of my bases are 10 and 15. So if you want to kind of double check that you're doing it right, you can tell, right, that these interior bases are getting doubled. The 3 is written twice, the 8 is written twice, the 10 is written twice, and the 0 and the 15 are the endpoints. So as long as the interior ones go through the ringer 2 times, I think you're good. Okay. So let's see. I think just mathematically, to save us a little bit of time, if this was a no calculator problem, you would work it out by hand, but you do get 418. And technically, I guess, if this is the integral from 0 to 60 of the velocity function, we have calculated a displacement. It's an approximation for the displacement over those 60 units of time. But it's not asking us that, so shut up, Miss Rand. Okay. Let's talk about over and under estimates of trapezoidal approximations. So back when we did rectangles, we knew that if a function was increasing or decreasing, that determined whether or not the approximation would be an over or under approximation. It's very different for trapezoids. So we have, anytime a function is concave up, whether it's increasing, as in this case, or if it's concave up and decreasing, as it is in this case, any trapezoid is going to fall above the curve. You see that there? If I connect any 2 points on this, it goes beyond the curve. It's what we call circumscribed, right? So anytime a curve is concave up, we have over approximations for trapezoids. And of course, if I do the opposite, if we have a curve that is concave down, increasing, or if we have a curve that is concave down, decreasing, any little trapezoid that I put in there, right, because of that concavity, is going to lie below the curve entirely. So it's going to be an under approximation. So concave down, under approximation. Yay, trapezoids. Okay, and usually to figure that out, I just sketch the function and draw one huge trapezoid so I can tell if there is or isn't space, right, between the function and the trapezoid. All right, let's see if we have time here for examples 4 and 5. Example 4, oh, adorable, a table of values, how shocking. This one gives us the volume of a spherical hot air balloon expands as the air inside the balloon is heated. Thanks, physics. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. So again, this is telling us the radius is measured by r, but then if we keep reading, it says For 0 to 12 minutes, the graph of R is concave down. Okay, so they're probably telling us that so that we can know whether or not it's an over or under approximation. But anyway, the table above gives selected values of the rate of change of R prime. So remember that they tell us about R, but then the table of values is about its rate of change, R prime. And this is, again, feet per minute. And the radius of the balloon is 30 feet when t equals 5. So there's an initial condition for us to work with if we needed it. They give us the volume of a sphere, yay geometry, and then the actual question says, use a trapezoidal approximation with 5 subintervals to estimate 0 to 12 r prime of t dt. Using correct units, explain what your calculation means in the context of the problem. So 5 subintervals, right, usually goes with 1, 2, 3, 4, 5, exactly how many data points there are. I mean, technically there's 6 data points, and that's why we have 5 subintervals. So if I do the same sort of calculation as before, I'm going to calculate these heights. Well, I guess, first of all, I want you to think about, is this equal heights in each of these trapezoids, or are the heights unequal? Okay, since the change in time is different between every any two values, we're going to go with individual calculations. So my first one is 2 over 2, and then the sum of the bases is 5.7 plus 4.0. My next one is 3 over 2. Again, just looking at the difference between 2 and 5, right, to get that 3 number that I'm using. 4 plus 2 are the heights. The next 2 is 2 over 2. 2 plus 1.2, 4 over 2, and that's 1.2 plus 0.6. And the last one is 1 unit in height over 2, and then the sum of those bases. Okay, I assume because of all the decimals, this would be a calculator problem, so I'm gonna go through that for you, assuming that if you were to type that on your own, you would make no mistakes and get the exact same number as I did. Now, it does ask us to explain what this calculation means, right? This is the area under the curve. So think about it again. We've got time on the x-axis, and we have feet per minute. I guess I should call this minutes on the x-axis. So if we're finding the area under this curve, right, with this approximation, what are we calculating, right? Feet per minute times minutes for what integration does, right? So I'm getting total feet. So this is the change in feet of the length of the radius between, we have to mention time, t equals 0 and t equals 12. Okay, the only reason I'm using that change in feet is because I'm thinking about the fundamental theorem, which means that this integral, when I calculate it to be 26.05 as an approximation, is actually r of 12 minus r of 0, right? And that's the change in the radius length over those 12 minutes. Right, so that's, you know, sometimes we say this phrase net change in feet. Maybe it'd be better if I put this in parentheses of the length of the radius. Okay, so overall, that's how much the balloon changed from 0 to 12 minutes. Okay, in radius. Okay, and then here's a combo platter. Example 5 takes us on a journey to do a couple things at once. We've got a metal wire that's 8 centimeters long. It's heated at one end. The table gives select values of temperature of the wire, x centimeters from the heated end. So if the wire is this long, here's 0 and here's 8 centimeters, this tells us, you know, if I'm here on the wire, how hot is the temperature right there? What are the degrees? So that's what distance for the x value means here. this question says, write an integral expression in terms of T of x for the average temperature of the wire. So this part is okay. Since I'm given temperature as my T function, I can go ahead and calculate the average over these 8 units of distance. So I would write 1/8 times the integral from 0 to 8 of T of x dx. So that is the answer to the first question in the purple. The second part says, then estimate the average temperature of the wire using a trapezoidal sum with 4 subintervals indicated by the data in the table. So now I'm going to trap it out, right, for these 4 subintervals here and do 4 individual calculations because all of the heights are different from one x value to the next. Okay, and then don't forget at the end of that, you do have to make sure you divide by 8. Okay, so when you do the trapezoidal approximation, you're just doing this part of the integral. Okay, and then you're going to put your trap approximation, right, times that 1/8 to give your answer to Edpuzzle. Okay, so get that calculator out and good luck. Accurate to 3 decimals, please. And also include units.